welcome back to Math 135. Today we're going to look at Lesson 12, Solving Equations with Advanced Factoring. We have worked with linear equations, we have solved rational equations, we've solved quadratic equations, and now we want to extend that into some slightly more complicated kinds of equations. Okay? So, getting started though, I like to go back and look at what we've done before. So the first equation that we have is down here on the bottom. X squared minus 13x plus 36 equals 0. And I have several questions that I want to kind of keep going throughout this lesson. How many solutions should you have to this equation? Well, we should have 2. And what tells you that there should be 2? Right here. This exponent tells us, he's a quadratic equation, tells us we should have 2 solutions. Then you stop and think, well, how do I go about solving one of these quadratic equations? Well, I can solve by factoring. I can solve by completing the square. I can solve by using the quadratic formula. So you have 3 options. And the question I asked is, well, which one would be the most efficient? Might as well save time. Well, you know, the answer to that is going to be dependent upon you. Personally, I'm not going to do complete the square unless I'm absolutely forced to. I can use the quadratic formula, but there's a lot of simplifying. If I can, this is my favorite. But for some of you, that may not be your most efficient. So let's go ahead and solve him. If we're going to solve him by factoring, it factors pretty nicely to x minus 9, x minus 4 is equal to 0. And then remember we talked about the zero product property and how that tells us that since these 2 quantities are being multiplied to get an answer of 0, we know that x minus 9 is 0 or x minus 4 is equal to 0, and we find our 2 anticipated solutions of 4 and 9. Okay, well that wasn't too bad, and that's just kind of review of what we just did with our quadratic equations. Well then let's extend that and look at this equation. You'll notice that he looks a lot like the last guy, only those exponents are running just a little bit differently. Now, up at the top, I said this is a quadratic form. It's not a quadratic equation, but it's a quadratic form of an equation. And the reason that would be is if you take x squared and you square it, remember what you do when you raise a power to a power? You multiply those guys. There we go. Okay. Now, by the way, how many solutions should we get? I always like for you to be thinking about that at the beginning of the problem, okay, so that you know what to expect as you work through it. Well, this 4 indicates to us that there should be 4 solutions. And that comes about really from the fundamental theorem of algebra, okay, that kind of assures us that this is going to happen. Now, you do not have to do this substitution, but some of you may like to do this recommended substitution. So I'm going to show you the substitution. It is really going to be your choice. You must practice and see whether you are more successful with doing the substitution or more successful staying within the x's. Meaning, we've got x to the 4th minus 13x squared plus 36 equals 0. And I could decide, all right, we're going to let u equal x squared. Now the reason we would do that is that then this x to the 4th would be called u squared. And that x squared becomes u. And when you look at that equation, you notice that he looks exactly like this guy. The only difference is, well, it's a u instead of an x, but oh well. So u will equal 9 or u will equal 4. There's no need for me to really work through that all again. But I did put a reminder here for us. Be sure to go back into, if you substitute, go back into your original variable, because the problem didn't want to know what u was. I'm sorry, that grammar sounds awful, but it doesn't want to know what this substituted variable is equal to. It wants to know what the x is. So I substitute back in and I say, oh, then x squared is 9 or x squared is 4. Well, if x squared is 9, we've got two options for that. It could be plus or minus 3. Likewise, there are two options here. And look at what happened. How many answers do I get for x? 4. And that's what I would have anticipated from the degree of the polynomial from the very beginning. So that's very good news for me. And of course, I could test them by putting them back in. But we managed to solve a 4th degree, which is called a quartic. And by the way, just so you know, all quartics can be solved. Now, not easily, but they can all be solved. Once you get above 4th degree, then you're getting into really tough territory. Okay, well, let's make a little bit of a switch here, and now you'll notice that I don't have an exponent showing. Of course, there is an exponent here of 1, but then I also have that square root sitting in there. And what is really important for you to notice is that you have both the square root of x and x in the same equation. So it makes it very difficult to try to isolate the x. And you could square both sides, but if we don't have to go there, we won't. So I might just say, you know what, how about if I let u equal the square root of x. Now, the reason I picked that is that that is the lower exponent, the lower power, and if I square this, u squared will equal x. And so I have a nice substitution for both of those. And so when I do that substitution, I get 2u squared minus 7u is equal to 30. Now again, you may not like doing that substitution, but you know what's really nice about that is that now I'm looking at an equation that is a quadratic equation. We worked with those before. Quadratics hold no secrets. That quadratic formula makes sure every one of them is solved, and solved quite easily. So bring the 30 across. Why am I doing that? Yeah, I need the 0. If I'm going to solve a quadratic by the quadratic formula or by factoring, I must have the 0. So 2u squared minus 7u minus 30 is equal to 0. Well, now let's see here if this guy will factor. If he does, it'll be a 2u and a 1u. And let's see here. I think a 15 and a 2. Let's kind of double check. If I have a, no, that won't work, will it? That's a negative 15 and a plus 4. I could use a 1 and a 60, a 2 and a negative 30, a 3 and a negative 20. 4 and it won't, a negative 15, that's negative 11, 5 and negative 12, there we go. Okay, sorry about that. But you know what's nice about that is, hey, if it doesn't just jump out at you, sometimes you have to work at it. So this is going to be a 5 and this will be a 6. That will give me a negative 12 on the outside, gives me a 5 for the inside. You know, if it didn't factor, I still have that quadratic formula in my back pocket. But he did factor. And as we said, each of these factors equal to 0. Now, what am I applying when I set those equal to 0? That zero product property, right? u equals negative 5 over 2, or u will equal 6. But I didn't want to know what u would be equal to. I wanted to know what x would be equal to. So I need to substitute back in. So let's see here. U is equal to the square root of x. If I substitute that back in, let's go ahead and move over to the board. I've kind of used up my space there. We would have the square root of x is equal to negative 5 halves, or square root of x is equal to 6. Now, when you look at this, you realize you got a little bit of a problem there because that square root cannot come out as a negative value. This is the principal square root, and he's indicating you must have a positive value. So in fact, this is not going to be an acceptable solution. That sometimes does happen. So from here, we have the square root of x is 6, so x is equal to 36. Yes? No? Let's just double check it. You know, and especially since it was kind of a little bit of an awkward factoring and everything, if I'm ever the least bit unsure, man, I'm going to just kind of double check myself. So 2 times 36 minus 7 times the square root of 36, will that in fact equal 30? Well, we've got what, 72 minus, well, this is 6, so there's a 42. Yeah, we're good, right? Okay, so we found x is 36, all right? Okay, going on. Well, this gets even scarier looking. We have fractional exponents. And I know you may not have a whole lot of experience with fractional exponents, but you say, what in the world? Now, by definition, in case you haven't seen these fractional exponents before, x raised to the fractional exponent of m over n is equal to the nth root of x to the m. Now, there's also another way that may be more convenient. They're equivalent. It's the nth root of x, all of that raised to the mth power. Okay? Just so you know, in case you haven't seen it. And as it turns out, I know for some of you, you might look at a fractional exponent and say, what in the world? There are times in math when that is much more advantageous to work with. I do know, though, that a lot of times seeing the root, you feel a little more comfortable with that because you have seen the square root notation or the cube root notation more than you've seen fractional exponents. So in fact, x to the 2/3 really means the third root or the cube root of x squared. Okay, and x to the 1/3 would be the cube root of x raised to the first power. Okay, and you might feel more comfortable with that notation. Okay, well, then this is essentially this guy squared. Anytime you have that happening, and you'll notice it when this exponent is double this exponent. Anytime that's happening, you have a quadratic form to your equation. So you're going to substitute for the lower exponent. So we're going to let u equal x to the 1/3. Then if you square both sides, you get x to the 2/3. So we have u squared plus u minus 6 is equal to 0. And that's quite an easy thing to factor. So we say, how about u plus 3, u minus 2. I'll take just a second. Does that look right on the factoring? Yeah. So u would equal 3 or u would equal 2. But again, I don't want to know what u is, so I have to substitute back. I have x to the 1/3 is equal to, how about if that's a -3? -3, or x to the 1/3 is equal to 2. Okay? And you say, oh my goodness, what do I do then? Well, since you realize that this is that cube root of x, how would you undo a cube root? Well, you'd cube both sides. So x is equal to -27, or cubing that, x is equal to 8. Now you might say, well look, you didn't let a square root be equal to a negative value. Can we have a negative square root? I'm sorry, negative cube root? As it turns out, yes. Because if I take a negative value and I raise it to an odd power, I get a negative answer back. That isn't a problem with the odd roots. The problem is with the even roots. Okay? So in fact, we have 2 good answers. Yeah? That's kind of a scary looking equation. All right? Now, let me tell you what most students do on this. They look at this and say, ugh, it's awful. What I'm going to do is I'm going to square this out. I'm going to distribute my 11. Now, can you do that? Yeah. Now, should you? No. Let me tell you a couple of reasons why. First off, what you end up with is a 4th degree, a quartic equation. Now, you might recall that I told you a few minutes ago, yeah, they are all solvable. But that doesn't mean they're easy to do. Okay? So first off, you might get yourself into a really tough spot trying to solve this 4th degree equation. Secondly, you're asking for trouble, because I've seen many, many students over the years squaring binomials and making errors along the way. So you know, it's actually nicely set up to say, whatever this mess is, it's being squared and it's the same as here. It's actually beautifully set up to do a substitution. So let's do the substitution. We're going to let u equal this x squared minus 2x. And then this is very clearly going to equal u squared minus 11u plus 24. Now remember, once you get it into a quadratic equation, you have 3 options for solving it. If I can factor it, that's always my first choice. I can easily factor this guy, u minus 8, u minus 3. And I get 8 or 3. But remember, that's not what I was looking for. Okay, so I have to substitute back in. Now this is going to be quite a bit of work, so we'll come over here to finish this all out. We would have u equals 8 or u equals 3. Substituting back in, that means x squared minus 2x is 8, or x squared minus 2x is equal to 3. And let's solve each of those. I see a quadratic, means I need a 0, so bring that 8 over. Factors nicely. And we get 4 or -2. Now, by the way, I'm kind of skipping the little steps there of setting each of those factors equal to 0. I'm assuming that you're comfortable with that idea and can do that little step in your head. X squared minus 2x minus 3 equals 0. He factors x minus 3, x plus 1. Right? And that would give me 3 or -1. Now, by the way, I've got 4 answers here. Would we have anticipated 4 answers? Well, remember, I said in the very beginning, if you end up squaring this out, you take an x squared times an x squared, and you'll end up with a 4th degree. So there should be 4 solutions. And we've got those 4 solutions. -1, +3, -2, and +4. Okay? Well, now we're going to be doing some other kinds of polynomial equations, and first thing I want you to consider is when you look at 5x cubed equals 20x, how many solutions do you expect? I see a degree of 3. This is called a cubic, so I'm expecting 3 answers. And by the way, on this one, if you're working ahead just to see if you'll get it right, let's hope you came up with 3, because there is one thing that is sometimes done in this case that loses a solution for you. In fact, what I did is I gave you a big reminder here saying, man, this guy isn't a quadratic kind of thing. We're going to have to get them all set up and factor and so forth. Don't divide off that x. Some students say, well, I have an x on both sides. I can divide that off. You're in trouble when you do that. Now, by the way, you've got a 5 on each side. Can you divide that off? Yeah. And you say, what? Well, I'm fine with dividing both sides of this equation by 5. And you know, I would be fine with dividing both sides by x if you could assure me of one thing. Problem is, you can't assure me of that. What is it that we cannot divide off of both sides? 0. And because you don't know what x is, you cannot assure me that you are not dividing by a 0. So if you can avoid that, avoid it. And we can't. Okay. So what would I do with 5x cubed equals 20x? Well, let's go ahead and divide the 5 off. No reason really to carry it. So we've got x cubed is equal to 4x. Bring the 4x over to the other side. Why would I do that? Because I want the 0. I'm hoping that I can do some kind of factoring over on this side. So I can, in fact, pull out greatest common factor of x. And that leaves me with x squared minus 4. And then I look at that and I say, oh, I am home free. Now, some people like to go ahead and set each of these equal to 0 and solve, but if you're not careful, you're going to lose another solution. So factoring is a very safe way of trying to make sure you don't lose any solutions. And this x squared minus 4 factors as a difference of squares. So I have 3 factors here, all multiplying together to give me 0. So x is 0, or x minus 2 is 0, or x plus 2 is 0. So I have 3 answers. Okay? And if you had divided that x off in the very beginning, you would have lost that solution. And if you look at the beginning equation, yes, if x is 0, you get a 0 on both sides, and that is an acceptable solution to the equation. Okay? So, do be careful. Don't divide variables off. You can divide numbers all day long, but don't divide variables. Okay? Well, we got another 3rd degree equation, but this one has a new twist in it, in that I've got a z cubed, a z squared, a z, and a number by itself. This is a lot of junk. How many answers should we be looking for? 3. Is this quadratic-like? No. Do you see a common factor? No, I got lots of z's, but unfortunately this guy doesn't have one. So you decide, well, I'll move these two guys over. And I have 9z to the third plus 9z squared minus z minus 1. And you might look and look and look and look at that and say, I don't know how to factor that. Hey, by the way, this is a third degree cubic. All cubic equations can be solved. Okay? Just not all done easily. But this one is easy in that if I look really carefully, I might notice that, hey, I could do some factoring. I just can't factor all 4 of them all at once. It's a little too much information for me to process. But I can look at these first 2 and I can say, you know, I could factor in 9z squared out of those 2. Now, I know you might be saying, but you're not allowed. Well, if I'm careful about how I write it, I am. What I do is, inside of these parentheses, I put the 2 terms I would need to be able to multiply them back and get that. That's totally legal. Now, I look at the last 2 terms, and I say, is there anything I can factor out of those 2? I say, well, 1. And then as I look, I think, oh, what if I take a negative 1 out? So I said, I factor out a negative 1, and that would leave me with z plus 1. Hey, and by the way, if you're a little bit uncomfortable with it, realize that if I distribute that back, this is exactly what I get. Now you might look at that and say, well, that's just craziness. Doesn't get me anywhere good. Oh, but if you look carefully, you might notice that I essentially have got 2 really big, ugly terms. And so if you look at those 2 really big, ugly terms, there happens to be a common factor. And that's really nice when that happens. It doesn't always, but it's nice when that happens. Because you say, look, this guy has a z plus 1, and this guy has a z plus 1. So what can I do? Factor him out. So I put a z plus 1 out in the front, and then I say, okay, z plus 1 multiplied by what would give me this first mess? 9z squared. Okay? Z plus 1 times what will give me this last mess? A negative 1. Yay! And see, what's really nice is I am home free at this point in time because I've got a linear factor and I have a quadratic factor. Both of those are very easy for me to work with. As it turns out, this guy will nicely factor. I have 0 equals z plus 1. Here's a difference of 2 squares. 3z minus 1, 3z plus 1. Now I've got it down to 3 linear factors, which are very easy to solve. You set each one of these guys equal to 0, and when you solve those, we end up with z is, from here, can you process that much? Negative 1. From here, add 1, divide by 3. And from here, subtract 1, divide by 3. And is that what we would have expected in the beginning? 3 answers? Okay, so sometimes you may have to do your factoring, only the way we may have to factor if you see 4 terms. If you see 4 terms and you're thinking, oh my goodness, what am I going to do? Try to pair them up and see if by factoring greatest common factor out of the first two and greatest common factor or a common factor out of the last two, if we can get the same remaining factor, that will be very handy. It'll get us where we need to be. Okay? Wow. Another equation. We take a look at it. I see a third degree cubic. Means I'm looking for 5 answers, right? Okay. And I see that I've got an x cubed, an x squared, an x, and a number by itself. I have 4 distinct terms there. So you know what? It kind of looks like that last guy, doesn't it? Yeah. So how about if I bring these guys over to the left, and we'd have x cubed. Now I'm going to put them in decreasing order of exponents. So this would come over as a minus 5x squared. And this will have to be added over plus x. And I have that minus 5. Okay? Well, if we factor by pairs, since I've got 4 terms, and I don't generally factor with 4 terms. So I try working with the first 2 and the last 2, and I see that these guys have a common factor of x squared, and that leaves me with x minus 5, which is very nice, because that's exactly what I have right here. And so you might say, well, what do I factor out? A 1. And you don't have to, but I like to write it sometimes just so that I can clearly see what's going on. And remember that after that first step, what you have is 2 really big, ugly terms. And as you look at each of those, you say, well, hey, I have a common factor here of x minus 5, and that is being multiplied by x squared and plus 1. Yay! Then you look at this and you say, I've got a linear term, I've got a quadratic term, so I'm good to go. And how about if we try to factor that? And as you look and you look and you look, you realize that's a sum of 2 squares. And a sum of 2 squares is a prime polynomial as far as real numbers is concerned. So I could say, all right then, x minus 5 equals 0, or x squared plus 1 equals 0. Well, that means that x equals 5, or x squared equals negative 1. You remember what we do with that? You know, to get the x by itself, I'm supposed to square root it, but you're like, what? I have a negative 1 over there. Yeah, it's not going to be a real number. As it turns out, I can square root that, and I get, I'm sorry, how about x is equal to plus or minus the square root of negative 1. Remember, when you square root, you've got a positive square root and a negative square root. Now, we don't like to leave that as square root of negative 1. It makes us feel blech. So instead of that, we're going to put I. Okay. So we do have 3 answers to this particular equation. We have x equals 5, and we have x equals plus and minus I. Now, one of the things that I liked about this is it shows you the idea that my degree tells me how many answers there are. There are 3 roots to this, but they need not all be real. So interestingly enough, if you had y equals this particular polynomial, he would only cross your x-axis one time, you would only cross it at 5. You wouldn't cross it 3 times because there's one real solution and 2 imaginary solutions. So if you're looking for reals only, your answer is 5. If you're going to be open-minded enough to take the imaginary values as well, I have 5, I, and negative I. Okay? There we go. How about this guy? 3x to the 4th minus 81x is equal to 0. Well, you know, I could divide that 3 off, couldn't I? Because I see a 3 goes into 81. Can I divide the x off? Don't do that. Divide the 3 off if you like, and that leaves me with x to the 4th minus 27x is equal to 0. The nice thing about dividing off a number that's a common factor through there is that I get to work with smaller numbers. But don't divide the variable because you do not know what that variable is equal to, and you could actually lose solutions along the way. Hey, how many solutions should I have? I should have 4, right? Okay. Well, I could factor out a greatest common factor of, unfortunately, just an x, and that leaves me with x cubed minus 27. And then you look at that, and you look at that, and you look at that, and say, wow, how do I factor that? Well, you know, as it turns out, we have ways to factor what's called a difference of 2 cubes or a sum of 2 cubes. And you should have run into this in the past, but in case you have forgotten, let me tell you how these guys will factor and a little bit about how I remember it. If I have a cubed plus or minus b cubed, see, the reason for using the plus or minus is because I'm too lazy to write it twice, okay? And it's the same kind of a process. If I have a sum of 2 perfect cubes or a difference of 2 perfect cubes, it has 2 factors. One of those factors is a binomial, and that binomial is whatever cubed would give you each of those, a, b. And you keep the same sign. Whatever sign that was is the same in the binomial. Now the second factor is a trinomial. What's that? It means it's got 3 terms inside of it. The first term is this guy squared. Then I always jump out to the end. The last guy is that, the second one squared. And then the middle term is the product of these 2. And you're going to change this sign, minus, plus. Now, by the way, you might want to actually multiply those out to see how that interacts. Because as you'd multiply that a through this trinomial, and then you take the b through that trinomial, what you find is that you have some terms in there that have the same values but different signs, and they cancel out. That's why you need that middle term sitting in there. Okay? So you might want to just practice multiplying that so that you can feel more comfortable with this as a factoring form. All right? Okay, so then this, I notice, is a perfect cube. 27 happens to be 3 cubed. So it would be x, keep the same sign. What cubed gives me 27? 3. Then I've got the trinomial factor, which is this guy squared. The last term is that guy squared. And the middle is the product of these 2, so it's going to be a 3x, and it's going to be the opposite sign. Since this guy is a minus, it's a plus. Whew. Hey, by the way, one of the reasons why we have this trinomial is that You know, I explained about how you have terms in the middle there that will drop out. But the reason it gets left as a trinomial is because that guy is, in general, prime. Now, in special cases, he will factor, but in general, this guy is going to be a prime polynomial, all right? And what that means is, hard as I try, that's not going to factor. X squared plus 3x plus 9. And you could sit there and you could try the different options, and you will find he's not going to factor, all right? He's a prime polynomial. That means that I cannot break this down into 4 linear factors. But the good thing is, hey, as long as I can get it to quadratic, I'm good to go. So I say x equals 0. Hey, what am I applying here? The zero product property. These things multiply to give me an answer of 0. So this factor must be 0. Or the x minus 3 has to be 0, or this quadratic. X squared plus 3x plus 9 has to be 0. Now, of course, the first two are real nice and easy. X is 0, or x is 3. Now, if this guy doesn't factor, what do I have to do to get my solutions? Yeah, I need to go to the quadratic formula. Ugh. Well, we did it last time, so I thought it'd be a good review. Remember that's negative b over 2a, and my b value would be 3. So I have negative 3 over 2 times my a value is 1. Big old square root, and the first term inside is b squared minus. Remember I told you to kind of stress that minus. 4 times the a value times the c value, that would be a 36. All over 2 times a. Okay? I just plugged in all the values, taking the a, b, and c out of my quadratic equation. So x is negative 3/2 plus or minus the square root of negative 27 over 2. Oh, there's that negative underneath there again. Well, 27 will break down into 3 times 9. So you've got 3 times 3 times 3. And, of course, times that negative 1. So we would have a 3 coming out. The negative 1, in a sense, comes out as an I, because we don't like to have that negative under the radical. So we would have 3i on the outside, and this extra 3 stays inside. And there are my other 2 answers. Oh, that's kind of scary. So this particular 4th degree equation had 4 solutions. We get 0 and 3, nice, pretty ones, and they're real values. And then we get these 2 that are a little scarier looking, imaginary roots. Okay, so 2 real, 2 imaginary. By the way, one of the things you find is that when you have imaginary roots, they come in pairs. Okay, so let's kind of recap. We've hit some pretty hard equations here, and so you're really going to have to do some practicing. One of the things I want you to do as you get started is to be sure to check what is that highest exponent so that you know how many answers to anticipate. Then you ask yourself, if this is not just a real nice quadratic, is this quadratic form? Could I kind of substitute and turn it into a quadratic? And if so, consider doing that substitution in order to solve your equation. But hey, be sure to substitute back into your original variable at the end. Is this a polynomial that could be factored by grouping? And you generally recognize that when you've got 4 terms that cannot be combined, and then you try to pair them 2 and 2 and see if that can get you to a very favorable factoring. And the last thing that we noticed is that maybe you have a greatest common factor greater than 1, And specifically like on that last one when we could factor out the x, because if you can factor that out, you can get yourself down to a lower degree polynomial. You might be able to get yourself to a more reasonable polynomial, something that you could work with, okay? Oh, practice hard because these are really tough ones, and I will see you in the next session.